There is a planet that rises just before dawn and vanishes just after dusk, slipping in and out of the twilight, like something that doesn't quite want to be found. It has been circling our sun for 4.5 billion years. It was recorded by the ancient Sumerians. It confused the Greeks. It humbled the telescopes of Galileo. And even today, with spacecraft having visited it multiple times, having photographed every centimeter of its surface, having measured its magnetic field and its chemical breath. Even today, this world holds questions that have no satisfying answers. Welcome. If you found your way here to this quiet corner of the internet where we slow down and let the universe do the talking, then you belong here. This is Infinite Science, and tonight we are going to Mercury. Mercury is a planet of extremes, searing light on one side, absolute frozen darkness on the other, a surface scarred by billions of years of cosmic violence, a magnetic field that, by most conventional scientific logic, simply should not be there, an iron core so enormous and so disproportionate that it has challenged every model scientists have built to explain how rocky planets form. And, impossibly, given that Mercury orbits closer to the Sun than any other planet. Patches of water ice that have been sitting quietly in the polar shadows for millions, perhaps billions of years. Mercury is a world of paradoxes. The closest planet to the Sun, yet not the hottest. The smallest planet in the solar system, yet carrying one of the densest, most iron-rich interiors of any world we know. A world with almost no atmosphere, yet with a faint magnetic field that creates a real, if fragile, magnetosphere. A world that seems simple from a distance and turns out, on closer inspection, to be one of the most scientifically rich objects in the solar system. In this video, we are going to take the full journey. We'll cover the basics, the orbit, the temperatures, the paradox of Mercury's day and year. We'll walk the surface and peer into its geological history. We'll descend into the great iron mystery at the planet's heart. We'll trace the long arc of human observation, from ancient Babylonian tablets to the radio telescopes of the 1960s, to the spacecraft that have traveled there and sent back revelations. And we'll stand at the edge of what we don't yet know and look out into the questions that remain. The universe is patient. It has been waiting for us to understand Mercury for a very long time. Let us begin. Before we can appreciate the full strangeness of Mercury, and it is genuinely strange, as we will see, we need to build a foundation. We need to understand where Mercury sits in the solar system, how big it is, how it moves, and what it would feel like to stand on its surface. This is the chapter where we assemble the frame before we hang the paintings. Mercury is the innermost planet in our solar system. It orbits the Sun at an average distance of approximately 57.9 million kilometers. About 0.387 astronomical units, where 1 astronomical unit is defined as the average Earth-Sun distance of about 150 million kilometers. Put another way, Mercury is about 39% as far from the Sun as we are. If you scaled the solar system so that Earth were 1 meter from the Sun, Mercury would be about 39 centimeters away, barely the length of your forearm from our star. Mercury is also the smallest of the 8 recognized planets in our solar system. Its diameter is approximately 4,879 kilometers, just over 38% of Earth's diameter of about 12,742 kilometers. In terms of volume, you could fit roughly 18 Mercuries inside the Earth. In terms of mass, Mercury weighs in at about 3.3 times 10 to the 23rd kilograms. Only about 5.5% of Earth's mass. It is a small world by any measure, and yet And this is the first of Mercury's many surprises. It is not the lightest of the rocky worlds for its size. If you calculate Mercury's average density, you get approximately 5.43 grams per cubic centimeter. Earth's average density is 5.51 grams per cubic centimeter, almost identical. But Earth is a far larger planet, and larger planets compress their interiors more under their own gravity, which artificially inflates the measured density. If you correct for this gravitational self-compression and compare uncompressed densities, what the planets would be like if they were the same size, Mercury comes out significantly denser than Earth. It is, in this important sense, the densest planet in the solar system. That density is a clue, a loud, insistent clue about what lies inside. Mercury's orbit is one of the most eccentric of any planet. Eccentricity is a measure of how elongated an orbit is. 0 would be a perfect circle and 1 would be a parabola. Mercury's orbital eccentricity is about 0.21, which is the highest of any planet in the solar system. Pluto, if we include dwarf planets, is higher. This means that Mercury's distance from the Sun varies considerably over the course of each orbit. At its closest point, called perihelion, Mercury is about 46.0 million kilometers from the Sun. At its farthest point, aphelion, it is about 69.8 million kilometers away. That's a difference of nearly 24 million kilometers. As a result, the Sun appears about 1.5 times larger in Mercury's sky at perihelion than at aphelion. This eccentric orbit was, historically, one of the great scientific puzzles. Newton's law of universal gravitation does an excellent job of predicting planetary orbits. But not a perfect job, it turned out, for Mercury. Astronomers in the 19th century measured a small but persistent anomaly. Mercury's perihelion, the point in its orbit closest to the Sun, was slowly rotating around the Sun over time, a phenomenon called orbital precession. Most of this precession could be explained by the gravitational tugs of the other planets. But there was a small residual, about 43 arc-seconds per century, that classical Newtonian mechanics couldn't account for. Some astronomers proposed a hidden planet even closer to the Sun. They called it Vulcan. Despite earnest searches, Vulcan was never found. The real explanation came in 1915, when Albert Einstein published his general theory of relativity. His new framework for understanding gravity, which described mass as curving space-time itself, predicted Mercury's anomalous precession with extraordinary precision. Mercury, in this sense, became one of the first experimental confirmations of the most revolutionary theory in the history of physics. The little planet that no one could observe clearly turned out to be a testbed for our deepest ideas about the nature of reality. Now, let's talk about how Mercury moves, because this is where the genuine strangeness begins. Mercury completes one full orbit around the Sun in approximately 87.97 Earth days. That is a Mercury year, less than 3 months of our time. Mercury moves fast. At an average orbital speed of about 47.4 kilometers per second, it is the fastest moving planet in the solar system. The closer a planet is to the Sun, the more strongly the Sun's gravity pulls on it, and the faster it must move to maintain its orbit. Mercury, right on the Sun's doorstep, races through its orbit like a planet in a hurry. But here is where the paradox lives. How long does it take Mercury to rotate once on its own axis? You might assume the answer is 87.97 days, a perfect tidal lock, like our moon, which always keeps the same face toward Earth. That was actually the assumption for most of the 19th and early 20th centuries. It was wrong. The correct answer is approximately 58.65 Earth days. Those two numbers, 87.97 and 58.65, are in a precise ratio of 2 to 3. For every 2 orbits Mercury completes around the Sun, it rotates exactly 3 times on its axis. This is not a coincidence. It is a gravitational resonance, called a spin-orbit resonance, locked in place by the tidal forces of the Sun over billions of years. Mercury is not fully tidally locked the way the Moon is. It is locked into a more complex, subtler rhythm. 3 spins for every 2 trips around the Sun. The consequence of this resonance for anyone living on Mercury's surface, or anyone trying to keep time there, is bewildering. A solar day on Mercury, the time from one sunrise to the next, lasts approximately 176 Earth days. That is 2 Mercury years, packed into a single day. If you were standing on Mercury's surface and watched the Sun rise, you would wait nearly 6 months before it set again. And during your long wait, the planet would have completed 2 full orbits of the Sun. But there's more. Because Mercury's orbit is so eccentric, and because the planet's orbital speed varies so dramatically between perihelion and aphelion, faster when close to the Sun, slower when far. There are locations on Mercury's surface where the sky does something genuinely bizarre. As Mercury approaches perihelion, its orbital speed increases dramatically. At a certain point, near the closest approach to the Sun, the planet's orbital angular velocity actually exceeds its rotational angular velocity. The Sun, which has been slowly moving across the sky, appears to slow, stop, and then move backward, briefly reversing direction in the sky. Before the planet's rotation wins out again and the Sun resumes its normal march. To an observer at the right longitude, the Sun would appear to rise, stop, set back below the horizon for a moment, rise again, and then slowly arc across the sky. It is a sight that exists nowhere else in the solar system. Now, temperature. Mercury is the closest planet to the Sun. Surely it must be the hottest planet. Surely the searing solar radiation baking this small, unprotected world must produce the most extreme temperatures in the solar system. It does not. And the reason why is one of the most instructive lessons in planetary science. Mercury has almost no atmosphere. It has a thin exosphere, a scattering of atoms, but nothing that could meaningfully trap or redistribute heat. On the sunlit side of Mercury, the surface temperature can reach approximately 430 degrees Celsius, hot enough to melt lead. But without any atmosphere to hold that heat, the moment the Sun sets, the temperature falls off a cliff. On the night side and in permanently shadowed regions, temperatures drop to around minus 180 degrees Celsius. The total range, from scorching noon to frozen midnight, exceeds 600 degrees Celsius. No other planet in the solar system shows temperature swings of this magnitude. Venus, by contrast, orbits farther from the Sun than Mercury, but maintains a surface temperature of about 465 degrees Celsius, nearly constant day and night, pole to equator. Its thick carbon dioxide atmosphere and sulfuric acid clouds create a runaway greenhouse effect that traps the Sun's heat and distributes it uniformly. Venus is the hottest planet not because it is closest, but because it wears a heavy blanket. Mercury has no such blanket. It stands exposed to the full fire of the Sun and the full cold of space, alternately baking and freezing with every slow turn of its axis. This is Mercury in its basic outline. Small, fast, iron-rich, extreme, and already full of puzzles that will take the rest of this video, and much of the rest of this century's planetary science, to unravel. The surface is calling. Let us look more closely at the ground beneath our feet. stand on Mercury's surface. In your imagination for the moment, setting aside the problems of survival, and look around. The landscape is dramatic and austere. Beneath your feet, the ground is dark grey, pocked and cratered, scattered with rocky ejecta from ancient and not-so-ancient impacts. The horizon curves more sharply than on Earth. Mercury is a smaller world, and you can feel its diminutive size in the quickness of the horizon. Above you, the sun hangs enormous in a pitch-black sky, roughly 3 times larger in apparent diameter than it appears from Earth, blazing with an intensity that would be lethal without protection. No wind, no weather, no sound. Just the ancient, silent, scarred face of a world that has been accumulating its wounds for 4.5 billion years. Mercury's surface looks, at first glance, strikingly like the Moon. Both worlds are heavily cratered, geologically ancient, and marked by a long history of impact bombardment. For planetary scientists, this resemblance is scientifically meaningful. It tells us that both Mercury and the Moon record the history of the solar system's early violent period, before the reign of impact subsided and the inner solar system settled into the relatively quieter place it is today. But the closer you look at Mercury, the more it diverges from the Moon. The geology is richer and stranger. The processes that shaped it were different, and the record it has preserved of its own formation, internal evolution, and geological history is unique in the solar system. Let's start with the most obvious features: the craters. Mercury's surface is covered with impact craters ranging from tiny microcraters, barely visible at human scales, to enormous multi-ring basins hundreds of kilometers across. The largest and most spectacular of all is the Caloris Basin, which we will discuss in detail shortly. Craters on Mercury have somewhat different characteristics than craters on the Moon, because Mercury's higher surface gravity causes ejecta, the material thrown outward by an impact, to travel shorter distances. Mercury craters therefore tend to have ejecta blankets that don't extend as far from the crater rim as comparable lunar craters, but they are still awe-inspiring structures. Some of the larger craters show complex central peaks and terraced walls formed as the ground rebounds and slumps inward after the initial impact excavation. The naming of Mercury's craters follows a convention established by the International Astronomical Union. Craters are named after deceased artists, musicians, and writers who made significant contributions to their fields. Walking across Mercury's surface, in imagination, you would encounter craters named after Shakespeare, Beethoven, Tolstoy, Raphael, Hokusai, and dozens of other luminaries of human culture. The Hokusai crater, visible in radar imagery, is particularly striking. It shows a prominent system of bright rays radiating outward for hundreds of kilometers, suggesting it is one of the relatively younger craters on the surface. Distributed across Mercury's surface, covering large portions of the northern hemisphere and other areas, are broad expanses of smooth volcanic plains. These are not random. They represent ancient episodes of volcanic flooding, low-viscosity lava that erupted from vents and flooded across the landscape, filling in older craters and smoothing out the terrain. Messenger confirmed the volcanic origin of these plains through detailed analysis of their composition and their relationship to other surface features. The plains are younger than the heavily cratered terrain they cover, and they record a period of Mercury's history when the planet was geologically active and the interior was still warm enough to drive significant volcanism. Messenger also detected evidence of a different and more explosive style of volcanic activity: pyroclastic deposits. These appear in images as irregular, roughly circular pits surrounded by fan-shaped or diffuse bright deposits that are distinct from the surrounding terrain in color and reflectance. They are interpreted as the remnants of explosive volcanic eruptions, driven by volatile-rich magma that exhaled gas explosively as it approached the surface. Think of it like opening a soda bottle that has been shaken. The dissolved gas comes out all at once, propelling material outward. For Mercury to have had explosive volcanism, its magma must have contained dissolved volatile compounds, a fact that connects directly to the mysterious volatile-rich surface composition we discussed earlier. The explosive deposits are evidence that Mercury's interior was not entirely depleted of volatile materials, despite the planet's proximity to the Sun and its violent history. One of the most distinctive and scientifically important features on Mercury's surface are the lobate scarps, long, sinuous cliff faces that can run for hundreds of kilometers across the terrain, cutting through craters and plains with apparent indifference. Some of these scarps are several kilometers high, towering escarpments of ancient rock that would make dramatic scenery for any hypothetical explorer. The scarps are compressional features. They formed when Mercury's interior cooled and contracted, causing the planet to slowly shrink. As the planet shrank, the crust had to go somewhere. It couldn't just disappear. So it buckled and thrust upward along fault lines, creating these enormous cliff faces. The total amount of contraction implied by the volume and distribution of the lobate scarps is estimated at a reduction of Mercury's radius by between 5 and 7 kilometers since its formation. For a planet with a radius of only 2,440 kilometers, this represents a significant shrinkage. Messenger also found evidence of more recent, smaller scarps, suggesting that Mercury may not have finished contracting. The planet may still be slowly cooling and shrinking, its surface cracking and shifting in geological slow motion even today. Now, the centerpiece of Mercury's geological drama, the Caloris Basin. Caloris is one of the largest impact structures in the entire solar system. It is a circular basin approximately 1,550 kilometers in diameter, roughly the width of the continental United States from Chicago to the Atlantic coast. It was formed approximately 3.9 billion years ago when an object, an asteroid or a comet, of enormous size, perhaps 100 kilometers across, struck Mercury with incomprehensible velocity and energy. The explosion that resulted was many orders of magnitude beyond any nuclear weapon ever built. It excavated a hole hundreds of kilometers deep, threw mountains of rock thousands of kilometers into space, and sent seismic shockwaves tearing through the entire body of the planet. The name Caloris comes from the Latin word for heat. The basin was given this name because it sits near one of Mercury's hot poles, the 2 points on the equator that face directly toward the Sun at perihelion, when Mercury is at its closest approach and solar radiation is at maximum intensity. At these points, the Sun appears nearly 3 times larger in the sky than we see it from Earth, and the heating is extreme, even by Mercury's already extreme standards. It is a poetically appropriate name for a scar made by fire. Caloris was partially imaged by Mariner 10 in 1974, but the illumination conditions meant that only about half of the basin was visible during the flyby. Messenger completed the picture, revealing the full extent of Caloris and mapping its floor in detail. The interior of the basin has been extensively modified by later geological activity. It shows a complex mix of ridges, fractures, and volcanic plains, evidence of the geological processing that continued long after the initial impact. The floor of Caloris is a record of billions of years of tectonic and volcanic activity layered on top of one catastrophic event. The impact that created Caloris sent shockwaves around and through the entire planet. On the exact antipodal point, the point on Mercury's surface directly opposite Calauris, scientists found a region of dramatically disrupted terrain. The ground there is chaotic, jumbled, broken into a complex of hills and depressions that bears no resemblance to the surrounding landscape. This is called the weird terrain, or chaotic terrain, and it is believed to have been created by the focused seismic energy of the Calauris impact, which traveled through the planet's interior and converged with extraordinary intensity on the antipodal point, shattering the surface from below. No other feature in the inner solar system shows as clearly the sheer geological violence that one very large impact could visit on a small world. And now, the most improbable fact about Mercury's surface: water ice. Mercury's surface in places harbors water ice, preserved in the permanent shadow of deep polar craters. This is not a hypothesis or an inference. It has been directly confirmed by multiple independent lines of evidence from multiple spacecraft and ground-based observatories. How is this possible? Mercury's axial tilt is essentially zero, just 0.034 degrees from perfectly upright. This means Mercury's poles receive sunlight at an extremely shallow angle, and the floors of deep polar craters whose rims are high enough to block any direct sunlight, remain in permanent shadow. The temperatures in these shadowed regions are extraordinarily cold, between -170 and -200 degrees Celsius, colder than many of the outer solar system moons. Material that settles into these craters can remain frozen indefinitely. Water has been delivered to Mercury over its history by comets and water-bearing asteroids. When these impactors strike Mercury, the water they carry is mostly lost to space. But some fraction migrates across the surface, molecule by molecule, driven by temperature gradients and the random thermal motions of gas-phase water molecules, until it reaches a cold trap, a permanently shadowed crater where it freezes and accumulates. Over billions of years, even a small fraction of water from each impactor can add up to significant deposits in the polar cold traps. The evidence for Mercury's polar ice is compelling. Radar observations from Earth in the early 1990s detected unusually bright, radar-reflective deposits near Mercury's poles. Exactly the signature expected from water ice. MESSENGER's neutron spectrometer detected elevated hydrogen abundance at the poles, consistent with water ice. MESSENGER's laser altimeter confirmed that the ice-bearing deposits are precisely located in the permanently shadowed floor regions of polar craters. And visible light images of the polar regions revealed that many of the ice-rich areas are covered by dark material, now interpreted as organic compounds, complex carbon-bearing molecules that were delivered to Mercury along with the water by the same cometary and asteroidal impactors. Mercury is a planet of ice and fire, of blazing solar radiation and permanent frozen darkness separated by just the height of a crater rim. It is, in this way, a world of coexisting extremes, a theme we will keep returning to because it seems to be Mercury's defining characteristic. Beneath everything we can see on Mercury's surface, beneath the craters and the plains and the lobate scarps, beneath the polar ice and the volcanic deposits, lies an iron heart so enormous and so disproportionate that it has forced planetary scientists to rethink some of their most basic ideas about how rocky planets form. Let's start with what we know and work our way into what we don't. Mercury's average density, as we established earlier, is approximately 5.43 grams per cubic centimetre, nearly identical to Earth's and the highest of any planet if you adjust for internal compression. This density tells us with remarkable clarity that Mercury contains an unusually high proportion of dense material. In planetary science, the densest material that forms rocky planets in abundance is iron. Mercury must be iron-rich in a way that no other rocky planet is. But how iron-rich? The answer comes from a combination of measurements. Mercury's gravity field, the behavior of its magnetic field, precise measurements of its rotation rate, and the subtle wobble in its spin axis, and gravitational perturbations on its orbit. Combining all of these data sources, many of them refined enormously by MESSENGER, scientists have been able to model Mercury's interior structure. What the models tell us is striking. Mercury's iron core extends to a radius of approximately 2,000 to 2,100 kilometers. About 83 to 85% of the planet's total radius of 2,440 kilometers. The core constitutes approximately 55 to 60% of the planet's total volume. Earth's core, for comparison, extends to about 54% of our planet's radius and constitutes about 17% of Earth's total volume. Mercury's core is not merely large for a rocky planet. It is extraordinarily dominant, a vast iron sphere that leaves only a thin shell of rocky mantle above it. That mantle, the layer of silicate, rock sitting atop the core, is estimated to be only about 400 kilometers thick. On Earth, the mantle is nearly 3,000 kilometers thick. Mercury's mantle is barely a skin over its immense iron interior. And the crust above the mantle, the outermost rocky layer, is thought to be perhaps 35 kilometers thick in some regions. This is a planet that is, in its deep structure, almost entirely iron. Furthermore, that iron core is not entirely solid. MESSENGER confirmed what earlier theoretical work had suggested. Mercury's core is at least partially molten. The evidence comes from several sources. First, Mercury's magnetic field, which we'll discuss at length in the next chapter, requires ongoing convective motion in an electrically conductive fluid, which means at least part of the core must be liquid. Second, measurements of Mercury's rotation revealed that the planet wobbles slightly more than it would if its core were solid, a phenomenon that is consistent with a liquid layer allowing the overlying solid shell to rotate slightly independently of the deep interior. A small planet cooling over 4 billion years should by most expectations have developed a solidified core by now. The fact that Mercury's core is still at least partially molten suggests something is preventing complete solidification. The most likely explanation involves the composition of the core. If the iron in Mercury's core is alloyed with lighter elements, sulfur is the most commonly proposed candidate, based on MESSENGER's detection of significant sulfur on Mercury's surface. The melting point of the mixture is lower than that of pure iron. A sulfur-iron alloy can remain molten at lower temperatures, allowing the outer core to stay liquid even as the planet cools. This is similar in principle to the way that adding salt lowers the freezing point of water. Mercury's unusual core composition may be what keeps its dynamo running. And that brings us to the mystery. Why does Mercury have such an enormous iron core in the first place? 3 major hypotheses have been proposed, and none of them is fully satisfactory. The first is the primordial composition hypothesis. Mercury formed very close to the young Sun in a region where the early solar nebula, the disk of gas and dust from which the planets formed, was enriched in dense, refractory metals like iron and depleted in lighter, more volatile materials that would have been driven away by intense solar heating. Under this scenario, Mercury simply accreted from iron-rich planetesimals, and its large iron core is the natural result of forming from metal-enriched building blocks. This hypothesis has some appeal. It ties Mercury's composition directly to its location in the solar system, but it requires the composition of the early solar nebula near the Sun to have been much more iron-rich than current models of nebular chemistry comfortably predict. The second hypothesis is the hit and run, or giant impact hypothesis, which is currently the most favored among planetary scientists. Under this scenario, Mercury once had a much larger rocky mantle, similar in proportion to the other terrestrial planets. But early in the solar system's history, before the orbits of the planets had fully stabilized, Mercury suffered a catastrophic collision with another large protoplanetary body, perhaps comparable in size to Mercury itself, or even larger. This collision was not a direct frontal hit, but rather a grazing hit-and-run collision, in which the impacting body struck at an angle and then continued on its way, carrying off a large fraction of Mercury's silicate mantle materials. What remained was a planet stripped of much of its rocky exterior, with the iron core constituting a far larger fraction of the total than before. Computer simulations of this type of collision can reproduce Mercury's observed core fraction reasonably well, and giant impacts were undoubtedly common in the chaotic early solar system. Our own moon is believed to have formed from a giant impact between proto-Earth and a Mars-sized body. The physics of giant impacts is not in doubt, but here is the complication that makes planetary scientists lose sleep. If Mercury suffered a giant impact that stripped away most of its volatile-bearing silicate mantle, the planet should be severely depleted in volatile elements. Materials like sulfur, potassium, chlorine, and sodium that have relatively low boiling or evaporation temperatures. The intense energy of a giant impact would vaporize and drive off these volatile species. Yet MESSENGER found Mercury's surface is surprisingly rich in exactly these volatile elements. There is more sulfur, more potassium, more chlorine on Mercury's surface than simple giant impact models predict. This is a genuine contradiction between what the models expect and what the measurements show. Scientists have proposed various solutions. Perhaps the impacting body was itself volatile rich, and some of its material was accreted onto Mercury after the collision rather than being entirely lost. Perhaps the collision occurred at lower velocity, a gentle giant impact that stripped the mantle less efficiently and preserved more of the volatiles. Perhaps Mercury experienced multiple smaller impacts rather than one massive one, each stripping a little more mantle material without generating the extreme temperatures of a single catastrophic collision. None of these solutions is perfectly satisfying, and none has been definitively confirmed. The third hypothesis is the photophoretic or evaporative scenario. The idea that the early sun's intense radiation and solar wind physically drove off Mercury's silicate mantle material over time, leaving the denser iron core to constitute a larger fraction of the planet. This mechanism has some theoretical support, but faces challenges in explaining how enough material could be lost in this way, and how quickly, and whether it is consistent with Mercury's orbital history. The truth may involve some combination of all three mechanisms. An initial iron-enriched formation environment, modified by one or more giant impacts, with some subsequent volatile replenishment from later accreting comets and asteroids. Planetary science often works this way. The real history is more complex than any single clean hypothesis, and progress comes from slowly disentangling which processes contributed how much. What is clear is that Mercury's enormous iron core is the geological fact that explains almost everything else about the planet. It drives the magnetic field. It dominates the interior structure. It represents the largest unresolved question in the planet's formation history. And it makes Mercury unique among the rocky worlds of the inner solar system. A world defined at its heart by iron. Planets generate magnetic fields through a process called the geodynamo. In Earth's case, the outer core, a shell of liquid iron and nickel surrounding the solid inner core, convects vigorously. The combination of this convection with the planet's rotation drives large-scale, organized electrical currents in the liquid metal, and those currents generate a magnetic field. It is essentially a self-sustaining electromagnetic generator, powered by the heat flowing out of the planet's interior and regulated by the planet's spin. For a geodynamo to work, three things are required: a large reservoir of electrically conductive fluid, an energy source to drive convection in that fluid, and rotation. Earth has all three in abundance, and so does every other planet with a strong magnetic field: Jupiter, Saturn, Uranus, Neptune, and the gas giants. Mars and Venus do not have active global magnetic fields today. Mars lost its long ago, and Venus may never have had one, or lost it very early. Mercury should not have an active magnetic field. That was the expectation before Mariner 10. Mercury is small. Small planets cool faster, and a cooled planet has a solidified core, and a solidified core doesn't support a geodynamo. Mercury also rotates slowly, 58.65 Earth days per rotation, which was thought to be too slow to drive an organized dynamo. The scientific consensus before 1974 was that Mercury was magnetically dead. Mariner 10 changed everything with a single flyby. On March 29, 1974, as the spacecraft swept past Mercury's surface, its magnetometer recorded a clear, unambiguous signal: a global magnetic field. It was weak, only about 1% the strength of Earth's field at comparable distances. But it was real, it was global, and it was unmistakably dipolar in structure, with a North Pole and a South Pole much like Earth's. The science team was genuinely startled. A small, slowly rotating planet that conventional dynamo theory said should be magnetically dead was, in fact, running a real, active magnetic field. In the years since Mariner 10 planetary, scientists have developed models to explain how Mercury's dynamo can operate despite the planet's small size and slow rotation. The key insight involves Mercury's unusual core composition. As we discussed in the previous chapter, Mercury's core likely contains a significant fraction of lighter elements mixed with the iron, most probably sulfur, possibly silicon or other materials. These lighter elements lower the melting point of the iron alloy, keeping the outer core liquid even as Mercury has cooled over billions of years. The persistence of a liquid outer core, the convecting electrically conductive fluid that a dynamo requires, is the key to explaining Mercury's magnetic field. But if Mercury's outer core is liquid and convecting, why is the resulting magnetic field so much weaker than Earth's? This remains an active research question. One influential class of models invokes a special thermal structure in Mercury's interior. Specifically, the idea that the outer layers of the core, just inside the liquid outer core, are very stably stratified, meaning that fluid doesn't circulate through them easily. This stable layer acts like a filter or a damper on the dynamo below. The convection in the deep outer core generates a magnetic field, but before that field can emerge from the planet, it must diffuse through the stably stratified layer, and in doing so, it is smoothed out and weakened. Only a small fraction of the dynamo's output makes it to the surface. This deep dynamo model, developed by several groups of theorists, can explain both the weakness of Mercury's field and some of its other unusual properties. And those other properties are where the story gets even more interesting. Mercury's magnetic field is not centered on the planet the way Earth's field is. Earth's magnetic dipole axis passes through a point that is very close to the planet's center, offset by only about 450 kilometers, or roughly 7% of Earth's radius. Mercury's field is offset much more dramatically. Its dipole is displaced northward from the planet's center by about 480 kilometers, which represents roughly 20% of Mercury's radius. This is a significant asymmetry. The field is notably stronger in the northern hemisphere than in the southern, because the northern hemisphere is closer to the effective magnetic source. The practical consequence of this offset is dramatic. In the southern hemisphere, the magnetic field lines are more spread out, weaker, and more open. They connect more readily with the interplanetary magnetic field carried by the solar wind. This means that in the south, high-energy solar wind particles have much more direct access to the surface. The bombardment of Mercury's surface by solar wind ions and electrons is substantially more intense in the southern hemisphere than in the north. If Mercury ever had surface features that were sensitive to energetic particle bombardment, like certain types of volatile compounds, you might expect them to be preferentially preserved in the northern hemisphere. Interestingly, this is consistent with some aspects of Mercury's surface composition data, though the connection is still being investigated. Why is the field offset toward the north? The most plausible hypotheses invoke asymmetries in Mercury's interior, differences in heat flow, composition, or core solidification patterns between the northern and southern hemispheres. If the core convects differently on one side than the other, perhaps because the overlying mantle conducts heat away at different rates in different regions, the resulting dynamo could generate an asymmetric field. Some models specifically invoke differential solidification of Mercury's inner core. If the inner core is growing faster on one hemisphere than the other, this could drive asymmetric convection patterns in the overlying liquid outer core, leading to an offset magnetic field. Bepi Colombo, with its 2 spacecraft at different orbital altitudes, will map Mercury's magnetic field in far greater 3-dimensional detail than Messenger could achieve. Scientists expect this will allow much tighter constraints on the location of the effective magnetic source inside the planet, the structure of the dynamo, and the origin of the north-south asymmetry. Despite its weakness, Mercury's magnetic field does enough work to carve out a small magnetosphere, a region of space where Mercury's field pushes back against the solar wind. Earth's magnetosphere extends tens of thousands of kilometers in the direction away from the Sun and forms an enormous teardrop-shaped cavity in the solar wind. Mercury's magnetosphere is far smaller, only a few thousand kilometers in the sunward direction and somewhat larger on the night side, and it is constantly being battered by a solar wind that is 5 to 10 times denser and faster at Mercury's orbital distance than at Earth's. Messenger observed that Mercury's magnetosphere is extraordinarily dynamic. The process of magnetic reconnection, in which field lines from Mercury's field and the interplanetary magnetic field snap and reconfigure, releasing bursts of energy, occurs at Mercury far more frequently and far more intensely than at Earth. Messenger detected these reconnection events occurring up to 10 times more often than at Earth's magnetosphere, and each event injects large fluxes of energetic particles into Mercury's environment. The result is a magnetosphere in constant turmoil, never settling into the relatively stable configuration we enjoy at Earth. Mercury's magnetic field, then, is one of the most scientifically interesting features of an already scientifically interesting planet. Too weak to be explained by simple dynamo theory. Offset in a way that implies deep asymmetries in the interior. Operating in an environment of such intense solar wind that the magnetosphere is never at rest. And yet, there it is. A genuinely active, genuinely global magnetic field on a tiny, slowly rotating world that shouldn't have one. Mercury keeps defying its own limitations. When we talk about an atmosphere, we typically imagine something substantial. Layers of gas thick enough to create weather, to scatter sunlight into a blue sky, to breathe. Earth's atmosphere has 5 distinct layers and contains approximately 5.15 times 10 to the 18th kilograms of gas. Even Mars, with its thin atmosphere, has enough gas to generate dust storms that can blanket the entire planet. Venus has an atmosphere so thick that surface pressure is 92 times what we experience at sea level on Earth. Mercury has almost none of that. What it has instead is called an exosphere, a region so thin that it barely qualifies as an atmosphere at all, yet one that turns out to be scientifically fascinating in ways that a conventional atmosphere is not. The defining characteristic of an exosphere is this: the density of gas is so low that individual particles almost never collide with each other. In Earth's lower atmosphere, a given air molecule collides with its neighbors billions of times per second. In Mercury's exosphere, a particle might travel from the surface all the way into space without ever hitting another particle. Each atom or molecule lives its own independent life, following a ballistic trajectory determined by gravity and solar radiation pressure, with no fluid dynamics, no weather, no pressure gradients in any conventional sense. The total mass of Mercury's exosphere at any given moment is estimated to be less than 1,000 kilograms, roughly the mass of a small car. The equivalent surface pressure, if one could measure it meaningfully, is approximately 10 to the negative 14 bar. 100 trillionth of Earth's atmospheric pressure. This is a better vacuum than most laboratory experiments on Earth can achieve. The composition of Mercury's exosphere has been measured in detail, first partially by Mariner 10 and then comprehensively by Messenger. The species detected include hydrogen, helium, oxygen, sodium, potassium, calcium, magnesium, and several other trace elements. Each of these comes from a different source and behaves somewhat differently in the exospheric environment. Hydrogen and helium are largely derived from the solar wind, the stream of charged particles flowing outward from the Sun. Some of these particles are captured by Mercury's gravitational field and magnetic field, make their way to the planet's surface, become neutralized, and bounce back into the exosphere as neutral atoms. Hydrogen and helium atoms gained in this way are relatively lightweight and tend to escape from Mercury's weak gravity relatively quickly. Sodium is the most scientifically studied component of Mercury's exosphere, and for good reason. It is bright. Sodium atoms in Mercury's exosphere fluoresce. They absorb and re-emit sunlight at characteristic wavelengths in the yellow-orange, part of the spectrum, making them readily detectable from Earth with spectroscopes. This fluorescence creates what is sometimes described as Mercury's sodium tail, a faint, glowing extension of sodium atoms pushed anti-sunward by solar radiation pressure streaming away from the planet like a comet's tail, but composed not of dust and ice, but of atoms that were, until recently, part of Mercury's rocky surface. How do atoms get from the surface into the exosphere? There are 4 main processes, and they operate simultaneously, each contributing different species at different rates. The first process is photon-stimulated desorption. Photons from the Sun, particles of light, carry enough energy to physically knock atoms loose from the surface rock. This is the dominant source for sodium and potassium, both of which are loosely enough bound to surface minerals that a photon with sufficient energy can liberate them. The rate of this process is directly proportional to the intensity of solar radiation, which means it is highest at Mercury's subsolar point and weakest at the poles and on the night side. The second process is ion sputtering. The solar wind that bombards Mercury's unprotected surface consists of protons, alpha particles, and heavier ions traveling at several hundred kilometers per second. When these high-energy particles slam into surface rock, they can transfer their momentum to surface atoms and knock them free. a process called ion sputtering. This is particularly efficient at liberating heavier atoms like magnesium, calcium, and silicon from surface minerals, and it is a significant source of these species in the exosphere. The third process is thermal desorption. On Mercury's day side, the surface reaches temperatures of up to 430 degrees Celsius. At such temperatures, atoms that are only loosely bound to surface minerals can vibrate themselves free, gaining enough thermal energy to escape into the exosphere. This process is important for volatile species and operates most efficiently in the hottest regions of the day-side surface. The fourth process is micrometeorite impact vaporization. The constant rain of small dust particles and micrometeoroids striking Mercury's surface at high velocity generates intense local heating at the impact site, vaporizing both the impactor material and small amounts of the surrounding surface rock. The resulting cloud of atoms expands away from the impact site and contributes to the exosphere. This process provides a well-mixed sample of surface composition and is thought to be particularly important for supplying refractory elements to the exosphere. Simultaneously, material is being lost from the exosphere by several mechanisms. Atoms that reach escape velocity, about 4.25 kilometers per second from Mercury's surface, fly off into interplanetary space, eventually contributing to a diffuse cloud of material spread along Mercury's orbit. Atoms can also be lost by photochemical processes. Solar UV radiation can dissociate molecular species or ionize atoms, which then get swept away by the solar wind, and atoms can simply fall back to the surface, where they are reabsorbed into the rock and the cycle begins again. The result is a continuous dynamic equilibrium. Material is constantly being liberated from the surface and constantly being lost or reabsorbed. The exosphere is not a stable, well-mixed reservoir like Earth's troposphere. It is a perpetual waterfall, matter flowing through rather than sitting still. Messenger made several remarkable discoveries about the exosphere's variability. The composition and density of the exosphere change with Mercury's orbital position. When the planet is near perihelion, closer to the Sun, the more intense solar radiation and solar wind drive more atoms off the surface, and the exosphere becomes measurably thicker. There are also diurnal variations. The day-side and night-side exospheres have different compositions and densities because the processes driving supply, photon desorption, ion sputtering, operate mainly on the sunlit side, while the night-side exosphere is fed mainly by atoms bouncing over from the day side and by the lower energy processes of thermal desorption. Messenger also detected calcium in the exosphere, a somewhat surprising finding because calcium is a relatively heavy refractory element that wouldn't be expected to appear in large quantities through most of the standard supply mechanisms. The calcium abundance in Mercury's exosphere is higher than models predicted, and it varies in ways that suggest a connection to meteoroid impact events. This remains an active area of research. One of the most intriguing aspects of Mercury's exosphere is what it can tell us about the surface. Because the exosphere is, literally, material that has been recently liberated from Mercury's surface rock, measuring its composition is a kind of remote surface sampling. Messenger's measurements of the exospheric composition, combined with its direct measurements of surface rock composition, allowed scientists to build a more complete picture of Mercury's surface mineralogy than either measurement alone could provide. In a sense, Mercury's exosphere is the planet's own geochemical autobiography, written in atoms. Long before anyone knew Mercury was a planet, long before the word planet even existed in its modern sense, people watched the sky. They watched it every night because the sky was navigation, was religion, was calendar, was the ordering principle of the universe. They noticed with their unaided eyes that most of the lights in the sky moved together, rising in the east, setting in the west, slowly rotating through the seasons, but that a handful of bright lights wandered independently, following their own complex paths against the fixed background of stars. The ancients called these wanderers planets, from the Greek word for wanderer. And among the wanderers, one of the most elusive was the small, fast-moving light that appeared only briefly near the horizon at dusk or dawn, before vanishing back into the solar glare. The Sumerians of ancient Mesopotamia, writing on clay tablets more than 4,000 years ago, recorded observations of what they called Ubu Idim Gud Ud, a name that scholars associate with what we now call Mercury. The Babylonians, who inherited and expanded the Sumerian astronomical tradition, kept detailed records of Mercury's appearances in both the morning and evening sky, noting when it first became visible, when it disappeared, and its maximum elongation from the sun. They developed numerical methods, purely empirical, based on pattern recognition rather than physical understanding, to predict Mercury's appearances days and weeks in advance. These cuneiform tablets represent some of the earliest scientific observations in human history. The ancient Egyptians knew Mercury as well, and like several other ancient cultures, they initially treated it as two separate objects, one appearing in the morning sky and another, separately named, appearing in the evening sky. The planet was bright enough at its best apparitions to appear prominently, but its brief appearances so close to the sun made it easy to miss the connection between the morning and evening apparitions. This confusion is understandable. Standing on Earth's surface, you see Mercury in the west after sunset and in the east before sunrise, separated by weeks or months of invisibility. It takes careful observation and record-keeping to recognize that these are the same object. The ancient Greeks eventually made this connection. The pre-Socratic philosopher Heraclitus, writing in the 6th century BCE, argued that the morning and evening apparitions of both Mercury and Venus were the same objects, a recognition that separated Greek astronomy from its Egyptian and Babylonian precursors. The Greeks named the planet Hermes after the swift messenger of the gods, a name that, like the later Roman Mercury, captured the planet's quick, elusive behavior in the sky. The planet completes its full cycle of elongation from morning star to evening star and back, more rapidly than any other planet, moving through the full range of its appearances in just a few months. The Roman name Mercury stuck, and with it came the attribution of the planet to the fleet-footed divine messenger who served as a guide between worlds, a conductor of souls, a deity of commerce, communication, and quick thinking. It is a beautiful coincidence of mythology and astronomy, the fastest moving planet, named for the god of speed. Through the medieval period and into the Renaissance, Mercury remained poorly observed compared to the other planets. Its proximity to the sun made it difficult to observe. It is never more than about 28 degrees away from the sun as seen from Earth, which means it never rises more than a couple of hours before the sun or sets more than a couple of hours after it. Astronomers who wanted to observe Mercury had to do so in twilight, close to the horizon, through the thick and turbulent air that makes viewing conditions poor. Tycho Brahe, the great observational astronomer of the late 16th century, lamented that he had never managed to observe Mercury at all. The planet always seemed to escape him behind clouds or in poor seeing conditions. Galileo Galilei, who turned the first astronomical telescope toward the sky in 1609 and 1610, observed Mercury. But the results were limited. His telescopes were small, and the conditions for Mercury observation were unfavorable. he was unable to resolve Mercury into a disk the way he could Jupiter and Saturn, and he gained little detailed information. It was the discovery of Mercury's phases. Like Venus, Mercury shows a complete cycle of phases from crescent to gibbous to full as it orbits the Sun that proved most scientifically significant. Giovanni Zuppi, an Italian Jesuit astronomer, made the first clear observation of Mercury's phases in 1639, confirming that Mercury orbited the Sun inside Earth's orbit. A fact consistent with the heliocentric model of Copernicus, but incompatible with the geocentric model of Ptolemy, which had Mercury orbiting Earth. Over the following centuries, astronomers applied increasingly powerful telescopes to Mercury, with gradually improving results. The planet's small disk. Even at its largest, Mercury subtends an angle of less than 13 arcseconds as seen from Earth, roughly 1/150th the size of the full moon, made detailed surface observations extremely challenging. Nevertheless, by the 19th century, observers were beginning to produce sketchy maps of Mercury's surface, claiming to see bright and dark patches, and attempting to track their movement to determine the planet's rotation rate. The most influential of these observers was Giovanni Schiaparelli, the Italian astronomer who is also famous, or infamous, for his description of canali on Mars, which were later misinterpreted as artificial canals by enthusiastic observers, including Percival Lowell. In the 1880s, Schiaparelli made extensive observations of Mercury and concluded that it rotated synchronously with its orbit, one rotation per orbit, keeping the same face permanently toward the Sun, just as the Moon keeps the same face toward Earth. This conclusion was based on his tracking of surface markings that seemed to remain in the same position relative to the Sun. Schiaparelli's authority was considerable, and his conclusion was widely accepted for decades. Textbooks and popular science books of the early 20th century described Mercury as a world with a permanent day side of extreme heat and a permanent night side of frozen darkness. A dramatic, vivid image, but ultimately wrong. The correction came in 1965 from an unexpected direction. Radio astronomers at the Arecibo Observatory in Puerto Rico, using the immense 305-meter radio telescope that had just been completed, bounced radar pulses off Mercury's surface and analyzed the returning signals for Doppler shift. The Doppler technique measures how much the frequency of reflected radar is shifted by the planet's rotation. If one edge of the planet is rotating toward us, the reflected radar from that edge is blue shifted. If the opposite edge is rotating away, its reflected radar is red shifted. By comparing these shifts, Gordon Pettengill and Rolf Dice measured Mercury's rotation rate directly. The result? A rotation period of approximately 59 days, not 88 days. Mercury was not tidally locked. It was spinning faster than a synchronous lock would require. The 3-to-2 resonance, 3 rotations per 2 orbits, was the true answer, and it required a complete revision of the picture of Mercury's climate and surface conditions. One of the most spectacular events in the history of Mercury observation is the transit, the passage of Mercury directly across the face of the Sun as seen from Earth. Because Mercury orbits inside Earth's orbit, and because Mercury's orbital plane is tilted about 7 degrees relative to Earth's, Mercury passes between Earth and the Sun twice per orbit, but usually above or below the solar disk from our perspective. Only when Mercury happens to be at or near one of the 2 nodes, the points where Mercury's orbital plane intersects Earth's orbital plane. At the same time as it passes between Earth and the Sun, does an actual transit occur. This happens only about 13 or 14 times per century in May or November. Johannes Kepler predicted a transit of Mercury for November 7th, 1631. the first prediction of a Mercury transit ever made. The French astronomer Pierre Gassendi successfully observed this transit, becoming the first human to watch the tiny disk of Mercury move across the Sun. Gassendi was struck by how small Mercury appeared, far smaller than expected. The observation helped establish an accurate angular diameter for Mercury and contributed to an improved understanding of the scale of the solar system. Subsequent transits were observed with increasing precision. In the 18th century, the method of parallax, observing a transit from two widely separated locations on Earth and comparing the precise timing of contact, was proposed as a way to measure the Sun-Earth distance with unprecedented accuracy. Edmund Halley of Halley's Comet fame famously championed this method for Venus transits, but the same principle applies to Mercury transits. These observations gave humanity some of the first genuinely accurate measurements of the astronomical unit, the fundamental yardstick of the solar system. Today, Mercury transits can be observed safely by amateurs using properly filtered telescopes and solar projection methods. The most recent transit occurred on November 11, 2019, and was visible from much of North and South America, Europe, and Africa. The next Mercury transit will not occur until May 7, 2049. Watching a transit is one of those rare astronomical events that connects the modern observer to the long lineage of sky watchers who came before. Standing beneath the same sky, watching the same small dot move across the face of the same star, and feeling for a moment the patience and the wonder that science requires. In the mid-20th century, the dream of sending spacecraft beyond Earth entered the realm of the possible. The early years of the space age focused heavily on the Moon, understandably given its proximity and the extraordinary political stakes of the space race between the United States and the Soviet Union. But even as Apollo astronauts walked the lunar surface, NASA's planetary scientists were setting their sights on the rest of the solar system. Mars had been visited by the Mariner probes. Venus had been reached. Jupiter and Saturn beckoned. And Mercury, the innermost planet, the smallest, the one that even Tycho Brahe had failed to observe reliably, also beckoned. The fundamental challenge of sending a spacecraft to Mercury had been recognized early. Mercury is not simply far away. It is close, dangerously close to the Sun, and the Sun's gravity makes reaching Mercury surprisingly energy-intensive. A spacecraft launched from Earth carries Earth's orbital velocity of approximately 30 kilometers per second. To reach Mercury and not simply fall into the Sun or fly past, it needs to lose a great deal of kinetic energy relative to the Sun. This requires substantial fuel expenditure, or a clever alternative. The clever alternative was pioneered by Giuseppe Bepi Colombo, the same Italian mathematician after whom Bepi Colombo is named. Colombo recognized that a spacecraft could use the gravitational field of Venus to execute a gravity assist, swinging past Venus in such a way that the planet's gravity would curve the spacecraft's trajectory and alter its speed relative to the Sun, effectively acting as a free engine burn. By calculating the right approach trajectory, Colombo showed that a single Venus flyby could redirect a spacecraft toward Mercury with far less propellant than a direct trajectory would require. NASA adopted this idea for what would become Mariner 10. Mariner 10 was the 10th spacecraft in NASA's successful Mariner series, which had previously explored Mars and Venus. It was a relatively modest spacecraft by the standards of what would follow. A hexagonal magnesium frame about 1.4 meters across, topped by a high-gain antenna dish 1.37 meters in diameter, with two solar panels spanning 5.8 meters from tip to tip. Its total mass at launch was approximately 503 kilograms. Its scientific payload consisted of 2 television cameras for imaging, ultraviolet and infrared spectrometers for atmospheric studies, a magnetometer mounted on a boom for magnetic field, measurements, a plasma science experiment, a charged particle telescope, and a radio science experiment that used the spacecraft's radio signals to probe Mercury's gravity field and atmospheric properties. Mariner 10 launched on November 3, 1973, from Cape Canaveral aboard an Atlas Centaur rocket. The launch was successful, and the spacecraft immediately began transmitting data. During its cruise to Venus, it demonstrated a remarkable capability. By pivoting its solar panels to change the angle of reflected sunlight, it could use light pressure as a form of attitude control, a solar sailing technique that helped conserve its supply of attitude control gas. This technique would prove crucial for extending the spacecraft's life. The Venus flyby occurred on February 5, 1974. Mariner 10 passed within about 5,768 kilometers of Venus's cloud tops, and the gravity assist worked precisely as planned, redirecting the spacecraft toward Mercury. Along the way, the ultraviolet cameras captured extraordinary images of Venus's cloud structure, V-shaped wave patterns in the sulfuric acid clouds that were entirely invisible to ordinary cameras, but dramatically revealed in ultraviolet. The Venus flyby was, on its own, a significant scientific achievement. But the main event still lay ahead. On March 29, 1974, just 54 days after the Venus flyby, Mariner 10 made its first approach to Mercury, passing within about 703 kilometers of the surface at its closest point. The encounter lasted several days, during which the cameras transmitted more than 2,000 images of Mercury's surface. The images that came back were revelatory. For the first time in human history, people could see Mercury up close. The surface was heavily cratered, distinctly reminiscent of the Moon, but with its own character. The craters had slightly different morphologies. Ejecta patterns were more compact, and here and there were features that had no lunar parallel. The smooth plains, the lobate scarps. The Caloris Basin was partially visible, its western half caught in the incoming sunlight, while its eastern half lay in shadow. But even partially revealed, it was clearly an enormous impact structure, one of the largest in the solar system. And then the magnetometer spoke. As Mariner 10 swept through Mercury's vicinity, the magnetic field readings showed something that shook the science team: a clear, dipolar magnetic field. Not a localized anomaly, not a relic field in magnetized rock. A global, active magnetic field, weak but unmistakable. The planet that planetary science had said should be magnetically dead was, in fact, running a dynamo. After the first flyby, Mariner 10 continued on its orbit around the Sun. The orbital periods were perfectly synchronized. Mercury's orbital period of 88 days and Mariner 10's orbital period of approximately 176 days stood in a 2-to-1 ratio. Every 176 days, 2 Mercury years, Mariner 10 returned to the vicinity of Mercury, because the same hemisphere of Mercury was illuminated by the Sun during each return visit, a consequence of Mercury's own 3-to-2 resonance. The same side of the planet was presented to the spacecraft each time. The second Mercury flyby occurred on September 21st, 1974. This time the approach geometry was somewhat different, allowing different illumination angles on some terrain. More images were taken, the magnetic field was measured again and confirmed, and additional spectrometric data were collected. The second flyby added to the scientific return without significantly expanding the view of the surface. The unimaged hemisphere remained hidden. The third and final flyby took place on March 16, 1975. On this occasion, Mariner 10 came closer to Mercury than it ever had, within just 327 kilometers of the surface. This was the closest approach of the mission, and it allowed the instruments to gather their highest resolution data. The magnetometer measurements from this flyby provided the most detailed characterization of Mercury's magnetic field that would be available to scientists for nearly 4 decades. Additional imaging covered some new areas of the already imaged hemisphere at better resolution. By the time of the third flyby, Mariner 10 was running very low on attitude control gas, the nitrogen used to keep the spacecraft oriented correctly. Without attitude control, the solar panels couldn't track the sun, the antenna couldn't point toward Earth, and the instruments couldn't be aimed. On March 24, 1975, 8 days after the final Mercury encounter, mission controllers sent the shutdown command. Mariner 10's transmitter was turned off for the last time. The spacecraft fell silent. What Mariner 10 left behind was extraordinary and tantalizing in equal measure. It had mapped approximately 45% of Mercury's surface. A remarkable achievement for a mission that made only 3 brief flybys, but it left more than half the planet completely unimaged. The 45% it did image was the same 45% every time because of the orbital resonance. The hidden hemisphere would remain hidden for nearly 3 decades. The magnetic field had been discovered but could not be characterized in detail from 3 flybys. The exosphere had been sampled but not fully understood. The geology of the imaged regions had been documented but not interpreted in the depth that only orbital observation could provide. Mariner 10 was humanity's first handshake with the innermost planet. It was the beginning of an acquaintance that would take decades to deepen. After Mariner 10's final Mercury flyby in 1975, no spacecraft returned to Mercury for nearly 3 decades. This is not because no one was interested. Planetary scientists were acutely aware of everything Mariner 10 had left unanswered. The hidden hemisphere, the unexplained magnetic field, the uncertain geology, the uncharacterized exosphere. But the funding and political realities of space exploration are complex. Mars received enormous attention through the 1970s and 1980s. The outer planets were explored by Voyager 1 and Voyager 2. Venus received multiple Soviet and American missions. Mercury waited. The mission that would finally return to Mercury was selected in 1999 as part of NASA's Discovery program. A program designed to deliver focused, cost-effective planetary science missions. The proposal, from a team at the Johns Hopkins University Applied Physics Laboratory, was called MESSENGER: Mercury Surface, Space Environment, Geochemistry, and Ranging. The name was both an acronym and a deliberate homage. A messenger was Mercury's divine role, and this spacecraft would serve as humanity's messenger to the planet. The scientific goals were ambitious. MESSENGER aimed to map the entire surface of Mercury for the first time. It would characterize Mercury's geologic history, the timing and nature of volcanism, tectonism, and impact cratering. It would measure the composition of Mercury's surface, determine the properties of the core, investigate the nature of the magnetic field and the magnetosphere, characterize the exosphere, and search for evidence of volatiles in the polar regions. The engineering challenge was immense. Getting a spacecraft into orbit around Mercury requires shedding enormous amounts of kinetic energy, as we discussed when we talked about Mercury's orbital mechanics. MESSENGER's solution was a complex multi-flyby trajectory: 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys, spread over nearly 7 years of travel. each flyby using the planet's gravity to subtract speed from the spacecraft. The total trajectory covered approximately 7.9 billion kilometers, nearly 53 times the straight-line distance from Earth to Mercury, before the spacecraft finally arrived at its destination. Messenger launched on August 3, 2004, from Cape Canaveral aboard a Delta II rocket. The launch was flawless. The spacecraft's solar panels deployed and began producing power. The long journey had begun. The Earth flyby occurred on August 2, 2005, almost exactly 1 year after launch. The first Venus flyby followed on October 24, 2006, and the second on June 5, 2007. Then came the 3 Mercury flybys, January 14, 2008, October 6, 2008, and September 29, 2009. Each flyby was a scientific event in its own right, gathering data and revealing new portions of Mercury's surface for the first time. The first flyby alone imaged about 21% of Mercury's surface that Mariner 10 had never seen, including the region directly antipodal to Caloris, revealing the chaotic terrain in greater detail than ever before. On March 18, 2011, after 6.5 years and 15 planetary flybys and trajectory corrections, Messenger fired its main thruster for 15 minutes in a precisely calculated maneuver and slipped into orbit around Mercury. It was a historic moment. Messenger was the first spacecraft ever to orbit Mercury, and the science team at Johns Hopkins, watching the telemetry arrive across 96.3 million kilometers of interplanetary space, erupted in celebration that was both professional and deeply personal. These were scientists who had spent many years working toward this moment, and the moment had arrived. The initial orbit was a long ellipse that brought Messenger as close as 200 kilometers from Mercury's surface at its lowest point, and as far as 15,000 kilometers at its highest. This highly elliptical orbit was chosen partly for practical reasons. An orbital insertion at Mercury requires precise planning, and the elliptical orbit was the one that Messenger's remaining fuel could achieve. And partly for scientific reasons, since the low periapsis allowed close-range measurements of the surface, while the high apoapsis provided a wide-angle view of the magnetosphere. The discoveries came at an extraordinary pace. Messenger completed the global map of Mercury's surface, the hidden hemisphere, unseen since. Mercury formed 4.5 billion years ago, unknown to every human who had ever lived until Messenger revealed it, was finally photographed. The geology of the previously unseen side was broadly similar to the seen side: heavily cratered terrain, smooth volcanic plains, lobate scarps. But it had its own unique features, its own craters, its own geological character. Mercury was now fully mapped for the first time. The laser altimeter, called MLA, the Mercury Laser Altimeter, produced a detailed topographic map of Mercury's northern hemisphere, measuring surface elevation to an accuracy of a meter or so from orbit. The data revealed that Mercury's surface has significant topographic variation. The Caloris Basin is lower than the surrounding terrain. The polar regions show characteristic signatures of the permanently shadowed craters, and the global shape of the planet contains subtle asymmetries that tell geophysicists about the distribution of mass in Mercury's interior. The IOM X-ray spectrometer measured the composition of Mercury's surface with unprecedented detail, detecting fluorescence from elements including magnesium, aluminum, silicon, sulfur, calcium, titanium, and iron. The results were startling. Mercury's crust has surprisingly low iron content, despite the planet's enormous iron core. This indicates strong differentiation, the iron sank efficiently to the core during Mercury's early molten phase, leaving an iron-poor crust above. More significantly, the surface is rich in volatile elements. Sulfur concentrations are much higher than expected. Potassium and chlorine are present in significant quantities, and sodium is abundant. These volatile-rich surface compositions are deeply inconsistent with the simple version of the giant impact hypothesis, which predicts that a high-energy collision would have driven off most of the volatiles. This single finding has generated more scientific papers, more theoretical debate, and more creative thinking about Mercury's origin than almost anything else Messenger discovered. The gamma-ray spectrometer confirmed and extended the X-ray findings, detecting carbon, oxygen, sodium, magnesium, and other elements in the surface material. Notably, the detector detected elevated hydrogen abundance at the polar regions, a direct chemical signature of water-bearing material, confirming that the radar-bright polar deposits contain hydrogen-rich compounds, consistent with water ice. Messenger's cameras, working in combination with the surface composition instruments, identified and documented the pyroclastic volcanic deposits scattered across Mercury's surface. The explosive eruption remnants that indicate a volatile-rich interior capable of driving eruptions through gas exsolution. These deposits were not expected based on pre-Messenger models and required a revision of understanding about Mercury's volcanic history. The magnetometer produced a comprehensive, three-dimensional characterization of Mercury's magnetic field, confirming the northward offset of the magnetic dipole from the planet's center and measuring the field's variation with altitude, latitude, and longitude in far greater detail than Mariner 10's 3 brief flybys could achieve. Messenger also observed extensive magnetospheric dynamics, magnetic reconnection events occurring at very high rates, energetic particle injections, and complex interactions between Mercury's field and the highly variable solar wind. By 2012, Messenger had completed its primary one-year mission and was extended to continue operations. A second extended mission followed in 2013 and a third in 2014. As the extensions continued, the spacecraft's orbit evolved. Perturbed by solar gravity and radiation pressure, the periapsis altitude slowly dropped. By the end of the mission, Messenger was skimming Mercury's surface at altitudes of only 5 to 25 kilometers during its closest approaches, providing resolution that no one had ever imagined possible from orbit. Images taken during these final months showed Mercury's surface in extraordinary detail. Individual rocks, small craters, subtle color variations in the surface material. The end came on April 30th, 2015. Messenger's fuel, carefully rationed and squeezed over 4 years of operations, was finally exhausted. The spacecraft could no longer maintain its orbit. At 3:26 p.m. Eastern Time, Messenger struck Mercury's surface at a velocity of approximately 3.9 kilometers per second, ending its mission by becoming part of the world it had spent 4 years studying. It is estimated to have created a new impact crater approximately 16 meters in diameter on Mercury's surface. A tiny addition to the billions of craters that already covered the planet, and a fitting memorial to one of the most scientifically productive planetary exploration missions in history. Messenger had answered the questions Mariner 10 had raised, and, as science always does, had raised new ones that would take the next mission, already in development, to investigate. The story of Bepi Colombo begins not in the 21st century, but in the 1970s, with an Italian mathematician named Giuseppe Colombo, known to his colleagues as Bepi. Colombo was a man of remarkable spatial and mathematical intuition, a specialist in celestial mechanics who had an unusual gift for seeing trajectories in his mind's way that computers of his era could barely calculate. It was Colombo who first recognized that Mariner 10, after its first Mercury flyby in 1974, could return to Mercury a second and third time if it was placed on the right orbit. He calculated that Mariner 10's orbit around the Sun, if carefully managed, would bring it back to Mercury's vicinity every 176 days in a perfect resonance. He shared this insight with NASA, who incorporated it into the mission design. Mariner 10's 3 Mercury flybys, all of which returned to the same hemisphere, were Colombo's gift to planetary science. Bepi Colombo died in 1984, but his name lives on in the most ambitious Mercury mission ever attempted, Bepi Colombo, a joint endeavor between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, that represents decades of international collaboration and an investment of approximately 1.65 billion euros. The mission was formally approved in the early 2000s and spent many years in development and testing. Its complexity is extraordinary. Bepi Colombo consists of 2 separate scientific spacecraft. The Mercury Planetary Orbiter, MPO, built by ESA, and the Mercury Magnetospheric Orbiter, MMO, also known by its Japanese name, MIO, built by JAXA. Combined with a propulsion module called the Mercury Transfer Module, MTM, which uses solar electric propulsion, ion thrusters powered by large solar panels, to provide the thrust needed for the long journey to Mercury. Bepi Colombo launched on October 20, 2018 from the Guyana Space Center in Tiraudais, Kourou, French Guiana, aboard an Ariane 5 rocket. The 3 spacecraft components traveled together as a single stack for most of the journey, with the MTM providing thrust and the MPO and MMO in a partially dormant state, waiting for their moment. The trajectory, like messengers before it, required multiple planetary flybys to bleed off kinetic energy. 1 Earth flyby in April 2020, 2 Venus flybys, October 2020 and August 2021, and 6 Mercury flybys. The Mercury flybys began in October 2021. And even during these pre-orbital encounters, Bepi Colombo began collecting science. Several of the scientific instruments on the MPO and MMO were able to operate during the flybys, gathering data on Mercury's magnetic field, its particle environment, its surface properties in the visible and near-infrared, and its exosphere. Each flyby also allowed mission controllers to refine their models of Mercury's gravitational field, improving the accuracy of subsequent trajectory calculations. Mercury orbital insertion is targeted for late 2026, following the 6th and final Mercury flyby. Upon arrival, the transfer module will be jettisoned, and the MPO and MMO will separate and maneuver into their distinct science orbits. The MPO will enter a near-polar, roughly elliptical orbit with an altitude ranging from about 480 to 1,500 kilometers. A low orbit well suited to detailed surface mapping and geochemical measurements. The MMO will enter a more highly elliptical orbit, ranging from about 590 to 11,640 kilometers. A larger orbit that will carry it deep into Mercury's magnetosphere, allowing it to sample the particle environment, the solar-wind interaction, and the exosphere at a wide range of distances from the planet. The science payload of Bepi Colombo is the most comprehensive ever sent to Mercury. The MPO alone carries 11 scientific instruments, including a high-resolution camera system, MGNS/MCAM, for surface imaging, a stereo camera for 3D surface mapping, infrared and ultraviolet spectrometers for characterizing surface mineralogy and the exosphere, an X-ray spectrometer for surface elemental composition, a gamma-ray and neutron spectrometer for subsurface composition, a laser altimeter for topographic mapping, a magnetometer for magnetic field measurements, an accelerometer for gravity science, and a radio science experiment. The MMO carries 5 additional instruments optimized for magnetospheric and plasma science, including magnetometers, particle spectrometers, plasma wave sensors, and a sodium atmosphere spectral imager. Having 2 spacecraft simultaneously in different orbits around Mercury is one of Bepi Colombo's most significant advantages over Messenger. Messenger was in one orbit and could only sample the magnetic field and particle environment at one location at a time. Bepi Colombo's 2 spacecraft can sample 2 locations simultaneously, allowing scientists to distinguish between temporal variations, changes happening over time, and spatial variations, differences between locations. This is crucial for understanding the structure of Mercury's magnetosphere and the dynamics of its interaction with the solar wind. Bepi Colombo's science objectives can be summarized in several key questions that the mission is designed to address. First, what is the precise structure of Mercury's interior, and specifically, what is the size and state of the inner core? The MPO's radio science experiment and laser altimeter will measure Mercury's gravity field and rotation with far higher precision than Messenger, allowing scientists to model the interior in detail that approaches what seismology gives us for Earth's interior. Second, what is the full geological history of Mercury, from its earliest volcanism to its current state of tectonic quiescence, or near quiescence? Third, what is the 3-dimensional structure of Mercury's magnetic field and dynamo, and why is the field offset northward? Fourth, what is the complete inventory and distribution of volatile materials, including water ice, in Mercury's polar regions? And what do they tell us about the history of volatile delivery to the inner solar system? Fifth, how does Mercury's proximity to the Sun affect the solar wind and magnetospheric dynamics in ways that test our models of space weather? Bepi Colombo will also test fundamental physics in the strong gravitational field near the Sun. The precise tracking of the spacecraft's orbit, combined with detailed modeling of all perturbations, will allow scientists to measure the effects of general relativity, including the Shapiro delay, frame dragging, and post-Newtonian corrections, to higher precision than almost any previous experiment. These measurements probe the nature of gravity in the regime where Einstein's equations make strong, specific predictions. If there are any deviations from general relativity at this level of precision, Bepi Colombo stands a real chance of detecting them. The mission is expected to operate in Mercury orbit for approximately 1 Earth year, with possible extensions depending on the spacecraft's health and the science return. Given the intense thermal and radiation environment at Mercury, the solar panels must be carefully managed to avoid overheating, and the spacecraft must be shielded from the intense solar radiation. Bepi Colombo is an extraordinary feat of engineering. The thermal protection systems had to be designed for an environment 10 times more intense in solar flux than what Earth satellites experience. As of early 2026, Bepi Colombo is in the final stages of its approach, having completed all 6 Mercury flybys, and is in the process of final orbital insertion preparations. The planetary science community is poised for a new era of Mercury understanding. The questions that Messenger raised, and could only partially answer, are about to receive the scrutiny of the most capable Mercury mission ever launched. Bepi Colombo, the mathematician who calculated trajectories in his head and changed the history of Mercury exploration, would surely have had something beautiful to say about a mission bearing his name, carrying the most sophisticated scientific instruments ever sent to the innermost world Arriving 4 decades after the paper spacecraft he helped design last went silent. Science, like a trajectory, finds its way. In science, the most honest and exciting thing you can say is not, "We know." It is, "We don't know, but here is what the question looks like from where we're standing." Mercury is a planet full of those questions. Not the comfortable mysteries of complete ignorance, where we simply haven't looked, but the harder and more rewarding mysteries of partial knowledge, where we've gathered data carefully and found that the universe doesn't fit the frameworks we've built for it. Let us walk through the major open questions one at a time, with the care they deserve. The formation, mystery. Why is Mercury so dense, and why does it have such an enormous iron core? Is the oldest and most fundamental unanswered question in Mercury science. We have 3 categories of hypothesis: primordial iron enrichment, mantle stripping by one or more giant impacts, and photoevaporative or collisional loss of the silicate mantle over time. Of these, the giant impact scenario commands the most theoretical support and produces results in computer simulations that broadly match Mercury's observed properties. But MESSENGER's detection of high volatile abundances on Mercury's surface remains a major challenge for all simple versions of the giant impact model, which predict volatile depletion. The tension between the large core, suggesting violent stripping of mantle material, and the volatile rich surface, suggesting a less violent history or significant late volatile delivery, has not been resolved. Bepi Colombo will sharpen the constraints, particularly through better measurements of the interior structure and surface composition. But the fundamental puzzle of Mercury's birth may not be fully solved until we have seismic data from Mercury's surface, a goal that lies beyond Bepi Colombo. The volcanic history puzzle is the second major unsolved problem. We know Mercury was once geologically active. The smooth volcanic plains, the pyroclastic deposits, and the evidence of multiple episodes of eruption all testify to this. But precisely when did the volcanism occur? When did it peak? When did it cease? And why? The question of timing is particularly important because it constrains the thermal history of Mercury's interior. How quickly it cooled when the core solidified sufficiently to shut off the magmatic activity that fed the surface eruptions, and how that timeline compares with other rocky planets. Dating planetary surfaces is done through crater counting. Older surfaces accumulate more craters over time, so more heavily cratered. Terrain is generally older, but this method requires an accurate model of the bombardment rate. How many impactors of what size struck Mercury over what time periods? The bombardment rate is reasonably well understood for the early period of heavy bombardment, but more uncertain for the period from about 3.5 billion years ago to the present. MESSENGER's crater data have produced various estimates of the cessation of volcanism on Mercury. Some studies suggest it ended about 3.5 billion years ago, while others find evidence for more recent activity, extending perhaps to 1 to 2 billion years ago. The uncertainty is significant, and resolving it will require both better crater statistics and a better calibrated bombardment model. Bepi Colombo's global imaging will improve the former. The polar volatile mystery has multiple layers. We know water ice is at the poles. We know it is capped in many places by dark organic material. But the key questions remain open. How thick are the ice deposits? Are we looking at thin coatings on crater floors or meters-thick layered deposits? What is the exact composition of the dark organic material? Is it simple carbon-bearing compounds, or complex organic molecules of the kind that are thought to have contributed to the origin of life on Earth? And how stable are the polar deposits over geological time? Mercury's orbit evolves slowly under gravitational perturbations from the other planets, and the location and extent of permanently shadowed regions at the poles has likely changed over millions of years. Has the polar ice survived through these changes, or does it melt and refreeze? If ice can be lost and resupplied, what is the current budget? How much ice is arriving per year, and how much is being lost? These questions matter beyond Mercury. The same processes that sequester volatiles in polar cold traps on Mercury operate on the Moon and on asteroids. Understanding Mercury's polar ice, its history, its stability, its composition, illuminates a broader story about how volatile materials are transported and stored throughout the inner solar system, a story that ultimately connects to the delivery of water and organics to the early Earth. The magnetic field offset is the fourth major mystery. Why is Mercury's magnetic dipole displaced 480 kilometers northward from the planet's center? This northward offset produces a dramatic hemispheric asymmetry in the magnetic field. The northern hemisphere is significantly better shielded from the solar wind than the south. No other planet in the solar system shows such a pronounced magnetic field offset. The leading hypotheses invoke north-south asymmetries in the heat flux coming out of the core, which would drive asymmetric convection patterns in the liquid outer core and produce an asymmetric dynamo. But what causes the asymmetric heat flux? Is it a difference in the overlying mantle's thermal conductivity between north and south? Is it related to the pattern of core solidification? Perhaps the solid inner core is growing preferentially in one hemisphere? Or is there some other explanation entirely? Bepi Colombo's dual spacecraft magnetic field measurements will go a long way toward characterizing the field in 3 dimensions. By sampling the field at 2 altitudes simultaneously, scientists can better separate the contributions from different sources and build a more detailed picture of the underlying dynamo structure. But translating field measurements into a physical model of the dynamo, understanding what the fluid motions inside the core are actually doing, remains an extremely challenging inverse problem. The exosphere mystery involves several specific puzzles. One is the surprisingly high abundance of calcium in Mercury's exosphere, which is higher than most models predict and shows spatial and temporal variations that suggest a connection to meteoroid impact events. Another is the detailed mechanism of sodium, transport across the surface. How do sodium atoms released on the day side migrate to the night side and poles? And how do they contribute to the global sodium cycle? And a third is the question of whether the exosphere contains any species that haven't been detected yet. Species that might provide new information about the surface composition or interior processes. There is also the broader question of what Mercury can tell us about the general principles of rocky planet formation and evolution. We now know that rocky planets are common around other stars. Thousands have been detected, including super-Earths and sub-Neptunes that have no analogue in our own solar system. Many of these exoplanets orbit very close to their host stars, in environments not entirely unlike Mercury's. Understanding how Mercury formed, why it is so dense, and how it has evolved over 4.5 billion years in the intense environment close to the Sun gives us a template for understanding the innermost exoplanets, worlds we cannot visit or image in detail, but whose properties we can infer by analogy with Mercury. Mercury is, in this sense, not only an interesting world in its own right. It is a Rosetta Stone for understanding an entire class of planets throughout the galaxy. Dense, iron-rich, battered, magnetically active inner worlds, close to their stars, full of extremes. Every mystery we solve at Mercury is a mystery we partially solve for 1,000 other worlds we've never seen. Science is not only about the past, it is also a lens for looking forward at what we might learn, what we might build, what we might become. Mercury, for all that it is a world of deep geological time and ancient craters, also has things to say about the future, about where human knowledge is going, about whether, someday, human beings might stand on the innermost planet and look up at a sun blazing 3 times larger than it appears from Earth. Let's start with that last question, because it is the most vivid. Could humans ever visit Mercury? The honest answer is, theoretically, yes. Practically, it would be one of the most difficult human spaceflight missions conceivable with anything like current technology. The orbital mechanics challenge alone is enormous. As we've discussed, sending even a robotic spacecraft to Mercury orbit requires shedding vast amounts of kinetic energy, a challenge that demands either enormous fuel reserves or a multi-year, multi-flyby trajectory. A crewed spacecraft is far heavier than any robotic probe. It needs crew quarters, life support systems, food, water, radiation shielding, communication systems, and all the redundant backups that keeping human beings alive in space demands. The rocket capable of sending such a payload on a Mercury trajectory would need to be far larger than anything currently operational. The Saturn V, the most powerful rocket humans have ever successfully flown, would be challenged by a crewed Mercury mission. The Space Launch System, currently in development, might be marginally capable, but only with orbital refueling, advanced trajectory design, and technologies not yet fully developed. Once in Mercury orbit, landing on the surface would require propulsive descent. There is no atmosphere to use for aerobraking, as Mars offers with its thin but usable air. Every meter of descent from orbit to the surface would require burning fuel. The spacecraft would need to be entirely self-sufficient because communications delays, up to 13 minutes one way at maximum Earth-Mercury distance, rule out real-time guidance from Earth. And on the surface, the challenges multiply further. The thermal environment on Mercury's surface is among the most extreme in the solar system. The dayside surface temperature of up to 430 degrees Celsius exceeds the melting points of tin, lead, and zinc. Any habitat or spacesuit must provide effective insulation and active cooling against this heat while also protecting against the cold of night, which drops to minus 180 degrees Celsius. The solar radiation at Mercury's orbital distance is roughly 10 times more intense than at Earth, posing significant challenges for both photovoltaic power generation. Solar panels overheat and lose efficiency at extreme temperatures, and crew health. Even with shielding, the radiation environment is more challenging than at Earth orbit. And the long day-night cycle. 88 Earth days of continuous scorching sunlight followed by another 88 days of darkness would require either a power storage system of extraordinary capacity for the dark period or a habitat located near the poles where solar power is available more continuously. None of these challenges is physically impossible. All of them are engineering problems, and engineering problems can, in principle, be solved with sufficient technology, resources, and time. Scientists have published conceptual designs for Mercury crewed missions that address these challenges, using nuclear power instead of solar, employing advanced thermal management systems, choosing polar landing sites where temperatures are more moderate and permanently sunlit regions near the poles offer continuous power, and using fast transit trajectories made possible by advanced nuclear or electric propulsion to reduce the crew's exposure time in interplanetary space. The scientific motivation for a human presence on Mercury would be substantial. A geologist on Mercury's surface able to pick up rocks, chip at outcrops, deploy seismometers, and make observations that no remotely controlled robot can replicate, would learn in weeks what it takes robotic orbiters years to infer. Seismology alone measuring Mercury's interior via the vibrations of moonquakes, or Mercury quakes, would answer fundamental questions about the core structure and mantle properties that no other technique can address. Drilling into the polar ice deposits and sampling the organic material would yield scientific data of profound importance for understanding the chemistry of the early solar system. Direct sampling of Mercury's rocks would allow isotopic analysis and geochronology, precise dating of geological events, that remote sensing can never achieve. But a crewed Mercury mission is not on any space agency's current roadmap. The cost would be enormous, the risk to crew would be substantial, and robotic missions like Bepi Colombo can answer many of the most pressing questions at a fraction of the cost and with zero risk to human life. The realistic near-term future of Mercury exploration is robotic, and it is already underway. Beyond Bepi Colombo, what might come next? Several concepts have been studied at the early planning level. A Mercury lander mission, a stationary or mobile robotic lander that sits on Mercury's surface and measures its seismic activity, drills for subsurface samples, and monitors the exosphere directly from ground level, would be an enormous scientific advance. A Mercury polar sample return mission, landing in a permanently shadowed crater, collecting water ice and organic material, and returning it to Earth for laboratory analysis, would be transformative. The organics in Mercury's polar traps may include prebiotic molecules of the kind that contributed to the origin of life on Earth, and having them in terrestrial laboratories would allow analysis at a level of detail no spacecraft instrument can match. These are future missions, most likely decades away, but they are not pipe dreams. They are the next chapters in a story that began with ancient Babylonians scratching observations of a wandering light into clay, continued with Mariner 10's 3 brief encounters, expanded with Messenger's 4 years of orbital science, and is now advancing with Bepi Colombo's journey through the inner solar system. And perhaps the most important lesson that Mercury teaches us, the lesson that applies far beyond this one small world, is about the value of looking at the extremes. The hottest and coldest temperatures in the inner solar system on a single planet, the largest relative iron core of any rocky world, the most eccentric orbit of the classical planets, the magnetic field that shouldn't exist, the ice that shouldn't survive. The extremes are where physics is stress-tested. They are where the comfortable approximations break down, and the true behavior of matter and gravity and magnetic fields is revealed. Mercury is the universe's gift to those of us who believe that the most important scientific discoveries live at the boundaries, in the places where the conventional models fail, and something new must be imagined to take their place. Humanity has been looking at Mercury since before writing was invented. We are, right now, sending robots to orbit it and reveal its secrets. Someday, not soon, but not impossibly far either, human beings will stand on its surface and feel the weight of that enormous sun above them, blazing in a black sky over a cratered ancient landscape. And they will know that they are standing at the innermost boundary of the solar system, at the edge of the fire, on a world that has been keeping its secrets for 4 billion years. That will be a moment worth the wait. We began in the twilight, with a planet that barely shows itself before slipping back behind the sun's glare, patient and elusive and full of secrets. We end here in something that feels like a different kind of twilight, the edge of knowledge, where the light of what we understand fades gradually into the darkness of what we don't. Mercury has earned its mysteries. It is 4.5 billion years old, scarred by the violence of the early solar system, shaped by forces we are only beginning to understand. It carries in its iron heart a record of a catastrophic past, Whether that past involves a giant collision or an unusual formation environment, or some combination of processes we haven't fully modeled yet. It maintains, against all conventional expectations, a magnetic field. It holds water ice within sight, cosmically speaking, of the blazing sun. It keeps an exosphere that is constantly being born and dying, atoms rising from the rock and drifting back into it in a cycle that has been running for billions of years. 3 spacecraft have visited Mercury. Mariner 10 showed us the face of the innermost world for the first time. Surprised us with a magnetic field, showed us craters and plains and a basin of incomprehensible scale, and left us with more questions than answers. Messenger orbited Mercury for 4 years, mapped it completely, measured its composition, characterized its geology, refined our understanding of its magnetic field and exosphere and polar volatiles, and in the end became part of the planet by crashing into it at high speed. Bepi Colombo is approaching Mercury now, 2 spacecraft traveling together through the inner solar system, preparing to study the innermost planet with the most capable scientific instruments ever sent there. Each mission has been a conversation between humanity and Mercury, a tentative back and forth in which we ask questions, and Mercury answers in the language of data, of photons, of gravitational tugs, and magnetic whispers. The conversation is still going. It will continue for decades, perhaps centuries, as we learn to ask better questions and build better instruments to hear the answers. And somewhere in all of this science, in the density measurements and the spectrometer readings and the magnetometer traces and the laser altimeter profiles, there is something more than science. There is the simple, ancient, deeply human act of looking, of pointing ourselves at something strange and unknown and saying, "I want to understand. I want to know what you are." Not because it is useful, though it often turns out to be. Not because it will make us richer or more powerful, though knowledge sometimes does that too. But because the universe is there and it is strange, and that strangeness is beautiful, and beauty calls to us across the darkness. The Babylonians scratched Mercury's appearances into clay tablets without any idea that they were documenting the orbital period of a planet. Galileo tried and mostly failed to see Mercury through his small telescopes, not knowing that what he was straining to see was a world with a vast iron heart. Einstein calculated the precession of Mercury's orbit and realized that his new theory of gravity predicted the number exactly, and he later said it gave him heart palpitations. The engineers who built Messenger poured years of their lives into a spacecraft that would spend 6.5 years traveling to a planet smaller than some moons, and they wept when it entered orbit. Science, at its best, is an act of love. Love of the truth. Love of the mystery. Love of the universe that has produced, against apparently enormous odds, minds capable of asking questions and finding answers. We hope this journey has lit something in you, a spark of curiosity, a desire to know more, a renewed sense of wonder at the strange and improbable beauty of the solar system we live in. If it has, then consider subscribing to Infinite Science, where we will keep following these threads, from Mercury to the outer solar system, from the birth of stars to the nature of time itself. Leave a comment if you have a question or a thought. We read them, and your questions shape what we make next. And the next time you are outside near dusk or just before dawn, look toward the horizon, toward the glow of the setting or rising sun. If you look carefully and the sky is clear and you know where to look, you might catch it. A small, steady light, very close to the sun, there and then gone. Mercury, the fastest planet, the smallest planet, the most iron-rich planet, the planet with water ice at its poles and a magnetic field that shouldn't exist. The planet that scientists in 4000 BCE, 400 BCE, 1600 CE, 1974, 2011, and right now, today, have been trying to understand. Keep looking. Keep wondering. The universe is patient. It will keep waiting for our questions. Until next time, this has been Infinite Science.